All right, hopefully this is pretty straightforward. What we're going to be talking about today is definite integrals. And essentially all we are doing is finding the exact area under the curve. So we're going to be doing that without using what we're going to learn next, which is the fundamental theorem of calculus. But it's essentially what you need to know is that this integral right here represents the area between the x-axis and the function from x equals a to x equals b. You will not see those x equals because it could change based on what we are integrating in terms of, right? If this was 2 to 3 f of t dt, then this would be from when t equals 2 to t equals 3, right? So that's not always going to be an x equals or whatever. Just pay attention to what variable you are integrating in terms of as you move forward into later on calculuses. Okay, but that represents the area between the x-axis and the function. Whether it's positive area or whether it's a negative area, it's the area between the x-axis and the function itself. If I have an area that is above the x-axis, so if I'm talking about this area right here, that is a positive area. If I'm talking about an area below the x-axis, so I'm talking about an area right here, this is a negative area. So positives, negatives, they're still going to come into play with this stuff. We'll kind of see how those affect our graph as we look at the applications of these as well. Okay, so this first part is just set up an integral that evaluates the area of each function. So I'm doing it from 2 to 3 of my function f of x, whatever it is, d of x. That's it. That represents the area of between the x-axis and the function from 2 to 3. All right, moving on. Same idea. Even though there's like that little part at 2 that's not really, doesn't have an area, this is just the integral from 1 to 3 of g of x dx. Please do not forget the dx. Without the dx, this is not an integral. You will not receive points if you do not put that dx or whatever you are integrating in terms of. Okay. Sketch the region where, all right, area is what I'm guessing I meant to write, where area is given by the definite integral, then use a geometric formula to evaluate this area. So I am doing the area under the line y equals 6 from -4 to 6. So this is y equals 6 from -4 to 6. And I'm trying to find all this area right here. So nice thing is that this is essentially just a rectangle. And this is a rectangle, so the area would be 10 times 6, which would be 60 units squared, since we were talking about the area defined by the definite integral. We're not always going to have units squared for integrals, depending on what situation we're looking at. So just know in this case it's talking about area, so I will say that this is in units squared. Yeah, that's it. It's a rectangle, so I use the area formula for a rectangle. Okay, so 2x from 1 to 3. Well, 2x goes like this, and if I'm going from 1 to 3, let's see, at 1 it is 2, right? Let me do this, 2, and at 3 it is 6. So the area here is going to be a little bit more complex to find, but it's not so horrible, because I mean this is essentially our trapezoidal rule, where my area would be, well, let me do it with my integral. So this would be what? Height times base 1 plus base 2 divided by 2. So my height is 2 units, because this is 2 units right there, times base 1 plus base 2, so 2 plus 6 divided by 2, which would be 8 units squared. And that's it. 2 minus absolute value of x from -2 to 2. So let's see, 2 minus absolute value of x would look something like this. From -2 to 2, let's see, -2 is here, and 2 is here. So this is essentially just a triangle, right? And this is hitting at +2 there. So I just have base times height divided by 2. The base is 4 times height divided by 2. would be 4 units squared. Cool. And that's really it by graphing these things. And for this absolute value one, we're not going to really talk about the antiderivative of it, just like we didn't talk about the derivative of it. These are ones that it's going to be a lot faster to just think about the graph and think about how it interacts with finding the area and all that stuff. Okay, moving on. This one is actually a half of a circle. So if you think about this equation, y equals 25 minus x squared, square root. So if I square both sides, y squared equals 25 minus x squared, then x squared plus y squared equals 25. So it's just a circle centered at the origin with a radius of 5. Since I only have the positive part of my square root, I just have the positive part of my function. So my radius is 5 units in any direction. So the nice thing here is I'm going from -5 to +5, also has a height of 5. But really, all I need to know about all this stuff is just the radius, because it's a circle and it's a half a circle. So pi times 5 squared divided by 2 because half a circle. So 25 pi over 2 units squared. And that would be it. Okay. Evaluate each integral using the following values. So here's kind of some characteristics that we're going to learn about this stuff. But it's giving us these terms, right? It's giving us those integrals to work with. They are true in this case. Except for, no, yeah, that should be right. Okay, so notice I have x cubed plus x. Well, this one is x cubed, this one's x. So this brings up a characteristic that we can do with our integrals, is that I can actually split them up with addition, as long as I write my dx, and I keep my interval the same. Then this becomes 60 plus 6, which would be 66, and that's it. And notice it's not asking for the area, so if I'm not asking for the area, I don't need to say unit squared in this one. Okay, I'm going to move on to part B. This constant in here, I can actually pull it out, kind of like how we treat derivatives, so I can treat this like 9 integrate from 2 to 4 of x dx. And the integral of x dx is 6, so this is really just 9 times 6, which is 54. All right, and I can treat the next one the same way too, right? So I could do for the integral from 2 to 4 of dx, and that is just 4 times 2, because here's my integral of dx, so this would just be 8. And that's it. I cannot multiply functions together. That is a no-no. That'll be something that you learn the first part of BC. So like if I had x cubed times x dx, that is not as easy as just doing 60 times 6. So this is not equal to, no bueno, please do not do this. Cannot do that. No, 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 no. I only tell you that so that you hopefully don't do it when it comes up. Because I've seen many a student do it in the past, and that's a no-no. Can't do that. That'll be something called integration by parts, which, like I said, it's going to be like day 2 of BC content. Okay, going on. So notice this one is going from 2 to 8. Well, I have an interval from 2 to 4 and from 4 to 8. So what I can do is I can actually add these together, because this is the same thing as saying from 2, the integral from 2 to 4 of f of x dx plus the integral from 4 to 8 f of x dx. Depending on our situation, it could be very nice to do that. Especially when you get into BC, you're going to have to do that with improper integrals. Okay, so from 2 to 4, that was 19 plus 12, so this is altogether 31. All right, notice here I'm going from 4 to 2. So from 4 to 2, what they're doing is they're reversing the order, and this actually just negates the area. So this becomes negative 19 units. It's going in the opposite direction. From 2 to 2, that is just trying to do the area under a point, no matter what my curve is. We don't really calculate the area of that straight line, so this would just be 0. There is no area under that curve. And again, that is if I'm going from the same x value to the same x value. I don't know an instance of when that would be useful, not off the top of my head, but just know that that's something that they could ask so that you understand what the area under the curve really means. Okay, that's really it. That's all I got for you guys. Should be pretty straightforward from the homework. So any questions you got, as always, let me know, and I will talk to y'all soon.